Yeah, if you look at K1, it's like 1.5 times 10 minus 3. K2 is 2.0 times 10 minus 6. So pKa1 is going to be close to 3, and pKa2 is close to 6. So just kind of your standard acid diprotic. Any other questions?
Yeah. If we have a diprotic like that, and let's just say we're adding it to 25 milliliters of NaOH,
Mm-hmm.
would the second equivalence point be at 25?
Yes.
Yes.
No. No. It would be 25 past the first equivalence point. And so if you're titrating, let's say you're titrating 25 milliliters of malonic at 0.100 with 0.100 molar sodium hydroxide, then the second equivalence point would be at 50 milliliters. It would require two equivalents, each equivalent being 25 milliliters.
Oh,
I don't know what I said in the problem. Let me take a look.
I think you had it properly about that.
Okay. If that's the case, then you would just, yeah, double. If both were 0.1, I don't think I tried to make your life difficult. So let me just take a quick look. Yeah, 0.100 and 0.100. So 10 milliliters of malonic acid. So it would take 10 milliliters of sodium hydroxide to reach the equivalence point, the first one. And then it'd take another 10 milliliters to reach the second one. So 20 milliliters would hit the second equivalence point. And the first thing you'd do is you'd analyze it. 5 milliliters would be half the first. 10 milliliters would be the first. 12 and a half would be 1/4 of the second. 20 would be the second. 25 would be 5 milliliters past the. Yeah, this would be excess strong base region. Okay. Okay, other questions? So are we good for tomorrow? Are there going to be requests for postponing till Thursday, or we're good for tomorrow?
Maybe we can move it to Thursday.
Do people want to move it to Thursday?
I think I know Jessica wanted to move Thursday.
Did anybody else want to move it, or do people want to keep it tomorrow?
Other than that, you want it Thursday.
Abby wanted it Thursday.
I mean, I already have another exam on Thursday, so it wouldn't make much of a difference, I guess.
Your preference would, Chase, would be for tomorrow.
Yeah.
Are we good for tomorrow then? Well, think about it. I'll survey you guys again here. Having two exams on one day is a pain. Okay, here's the practice test. If there are other questions on this, I can go through those. If not, I need to do some catch-up with Chapter 18. So today I had the lab, which is kinetics, scheduled. We're going to do, oh shoot, I just realized something. So we're going to do the kinetics lab on Wednesday, and then I'm going to fit in the electrochem lab as a demo probably in future date. So did we start chapter 18? The problems? What problem did we leave off on? What number?
Seven, maybe eight.
7, maybe 8. All right.
Seven.
7. Actually, I didn't do 7. I skipped it, but we could do 7. Let me go back to the book. All right, fluoridated drinking water contains about 1 part per million fluoride. Is calcium fluoride sufficiently soluble in water to be used as a source of fluoride ion for the fluoridation of drinking water? Explain. So if we're dealing with calcium fluoride, you know, fluorides, there are a lot more exceptions to these. So we have chlorides, bromides, and iodides grouped together, but fluoride, since there are many more exceptions, is better to look it up. The fluoride is very small, and so it has a high charge density, which means there are a lot more insoluble fluoride salts than there are chlorides, bromides, and iodides. And so it turns out that calcium fluoride is relatively insoluble. We can take a look at the KSP, and that'll give us an indication of the solubility. It won't tell us the solubility. We're going to have to calculate the solubility based on the KSP. But if we go over here, calcium fluoride has a KSP of 5.3 times 10 to the minus 9. 5.3 times 10 to the minus 9 is pretty small, so it's not very soluble at all. And we definitely call that an insoluble salt. But solubility is based on S, and so let's go ahead and calculate S. This is going to equal the calcium concentration times the fluoride ion concentration squared. Calcium fluoride is a solid, and so let's ignore that. The activity doesn't change, and just focus on this. So we're going to say that there's 0. And what we're going to do is we're going to add solid calcium fluoride and dissolve it in water. Saturate the solution. So this will be plus S, this will be plus 2S molar here. And so at equilibrium, we're going to have S molar and 2S molar here. And so this is going to be equal S times 2S quantity squared, which is going to give us 4S cubed. And therefore, the solubility of calcium fluoride is equal to the KSP divided by 4 to the 1/3 power. So I have the KSP here. Let's go ahead and calculate the solubility. So it's going to be 5.3 times 10 to the negative 9 divided by 4 equals, and then I'm going to raise this to the 1/3 power. And I get a solubility of 0.001098. This solubility is less than 0.1 molar, and therefore we call it an insoluble salt. So calcium fluoride is classified as insoluble, but is it soluble enough to supply 1 part per million fluoride? And so let's see. We can do a quick check for my calculation. The quick check is just plug it in here. So the calcium ion concentration is 0.001098 molar. And then I'm going to double this times 2. And the fluoride concentration is going to be 0.002196 molar. So what is this in terms of ppm? So I'm going to use some dimensional analysis, but before I do that, let's check my K to make sure this is correct. And so I'm going to take the fluoride ion concentration and square that, and then I'm going to multiply that by the calcium concentration, 1098. I get 5.298 times 10 to the minus 9. So it should be 5.3. I got 5.298. That checks out. So now I'm going to do a ppm. So I need to go from molarity to ppm. So I'm going to try to use dimensional analysis for that. And so I have 0.002196 moles of fluoride per liter of solution. Parts per million is in grams. So I need to know how many grams of fluoride I have. And so fluoride is 19.00 grams per mole. And then I'm going to go from liters to grams of solution. And so I'll go to milliliters, 1,000 milliliters per liter. And then I'm going to make an assumption. I'm going to assume the density of this solution is close to pure water. And so I'm going to say that I'm going to have, actually this is upside down, sorry. I'm going to say I'm going to have, for every 1 milliliter, I'm going to have 1.00 grams. And so let's go ahead and multiply this out. So it's going to be 0.002196 times 19 divided by 1,000. 4.1724 times 10 to the minus 5 grams of fluoride for every 1 gram of solution. So, you know, I could convert this into percentage, but the percentage is going to be very small. And so percentage is a part per 100. Part per 100. And so what I'm going to do is instead I'm going to convert it into a ppm. How do you go from this to a percentage, a fraction to a percentage? What do you do? To convert a fraction into a percentage, we multiply by 100%. However, to go from a fraction into ppm, we multiply not by 100%, we multiply by 1 million ppm. And so I'm going to take that and multiply by 1 million. And I get 41.72 ppm. In terms of percentage, it would have come out to 0.004172%. Is that right? Yeah, according to this. Well, anyway, I think I'm off. But anyway, the percentage is not as convenient as ppm, so we're going to use ppm. So I get the concentration of fluoride as 41.72 ppm fluoride. And so the question is this calcium fluoride salt soluble enough? And the answer would be what? Yes. Yes. It's soluble enough because I only need 1 ppm. And if I try to saturate the solution, I'm going to get up to 41 ppm. And so I just need to add just enough calcium fluoride to get it to 1 ppm, which means a lot less, if my calculations are correct. All right, let's do some other problems here. And so for this chapter, since we've been doing ice calculations quite a lot, we're just going to continue with these. Did I talk about number 11 and number 12? In chapter 17, we dealt with the acid-base titrations. In chapter 10, we're going to have a couple of other types of titrations here. Number 10 not number 10, number 11. Excuse me. Number 11, a 25.00 milliliter sample of a clear saturated solution of PbI2 requires 13.3 milliliters of a certain silver nitrate for its titration. What is the molarity of this silver nitrate? And so this is a precipitation titration. And so what we're going to do is we're going to analyze this for iodide concentration using silver nitrate. And so we're going to titrate the iodide with silver ions to precipitate out silver iodide. This is kind of tricky because what's the end point of this titration? The end point of this titration is when you've maxed out the precipitate. You know, when you've maxed out the precipitate, then you know you've precipitated out all the iodide. And then each additional drop of silver nitrate doesn't precipitate anything. But is it easy to tell when you've maxed out the precipitation? No, it's hard because you'd have to centrifuge it each time. You just get a white, cloudy solution. And so this is a pretty tough titration to do because it would require a lot of centrifuging after each drop, you know, to see when it stops precipitating. But anyway, this is something that we could do. You know, from the 13.3 milliliters and the 25 milliliters, we could figure out the concentration, figure out the amount. Okay, that's a precipitation titration. In number 12, this is a redox titration. Redox titration, I think, was covered in chapter 5 as well. This one is a lot easier to do the endpoint because calcium oxalate's colorless, but potassium permanganate has a big, heavy color to that. And this one, the endpoint of the titration is going to be when the color changes. And so basically, we're going to use permanganate. Permanganate is a strong oxidizer. It's going to be reduced to manganese 2. And then oxalate is going to be the reducer. Now, oxalate, when you look at the oxidation states, can you oxidize oxalate? And so what's the oxidation state of carbon in oxalate? +3? That's correct. +3. So yes, it is possible to oxidize this. Because what's the max on carbon? +4. And so we can oxidize this to the max, and that would oxidize to CO2. CO2 would be +4. So we can essentially oxidize this or burn this up to and get CO2. Over here for manganese, we're going from +7 to +2. Here. So this is an example of a skeleton redox, and then what we'll do is we'll balance this. So this is purple, and this is almost a very light pink, almost colorless. So when we see the purple color disappear, then it's going to go colorless. And so initially all the purple will disappear, and then when the purple persists, then there's no more oxalate. Oxalate's colorless, CO2's colorless. And so when the purple color persists, then that means there's no more oxalate to consume the permanganate, and we're at the end point. And so the end point for this number 12 is a lot easier. But again, this is a titration, just like you would do in chapter 5, I think it was. Okay, let's move on to number 15. Number 15 deals with the common ion effect. So we want to calculate the molar solubility of magnesium hydroxide in pure water. And then we're going to add common ion, magnesium and hydroxide, and see what happens to the solubility. Okay, whenever we're dealing with solubility that is dissolution or precipitation, we want to write out the KSP equation. So the KSP equation is going to be magnesium hydroxide solid goes to magnesium 2 plus 2 hydroxides. Here. The KSP for this is 1.8 times 10 to the minus 11. And this is going to equal the magnesium concentration times the hydroxide ion concentration squared. So part A, there's no common ion. And so we're just looking at the solubility in pure water. So what we do is we assume that we have plenty of magnesium hydroxide, and we dump that into water. Nothing's dissolved. But eventually what's going to happen is we're going to lose some of the solid magnesium hydroxide, and now we have to have enough that it completely saturates the solution so that we get plus S and plus 2S, where S is the max solubility. And we end up with S molar magnesium because it's in a 1-to-1 mole ratio with magnesium hydroxide. So S is the molar concentration of magnesium. It's also the molar concentration of how many magnesium hydroxide formula units we can dissolve in a liter of solution. And then we're going to have 2S. 2S is for the hydroxide. We're going to have twice as much hydroxide as magnesium, just due to the stoichiometry here. And so this is going to be S times 2S quantity squared. And so this is going to give us 4S quantity cubed. And then we can calculate what S is. S is going to equal KSP divided by 4, the cube root of that. And so I'll take my KSP, which is 1.8 times 10 to the minus 11, divided by 4, and then the cube root of that. And I get a solubility of 1.65 times 10 to the minus 4 molar. 1.65 times 10 to the minus 4 molar is less than 0.1 molar. If it's less than 0.1 molar, we call it insoluble. So we say that magnesium hydroxide is insoluble. Whereas it turns out that calcium hydroxide, strontium hydroxide, and barium hydroxide have solubilities greater than 0.1 moles per liter, which means we call calcium, strontium, and barium soluble, whereas magnesium would be insoluble. Magnesium is a much smaller cation than calcium, strontium, and barium, so you kind of expect its solubility to be lower than the others. But let's double check to make sure I didn't screw up the calculations. And so I need to double this, so times 2. The hydroxide concentration should be double, 3.30 times 10 to the minus 4 molar. And then we check our K value and see what that equals. So the hydroxide has to be squared, so I'm going to square that times 1.65 times 10 to the minus 4. And I get a K value of 1.798 times 10 to the minus 11, which is a good match. It should be 1.8. I pretty much got 1.8 times 10 to the minus 11. And so that seems okay. Now, what happens if there's common ion present? If there's common ion present, then we're not dissolving this into pure water. We're dissolving this into so the solid, we just got to make sure there's enough there. So I'm going to kind of ignore the solid and just go here. And so in part B, we have some magnesium there to begin with. And so how much magnesium do we have? 0.0862. 0.0862 molar. And then hydroxide 0 molar. And now we'll let it dissolve. Well, not as much is going to dissolve because of the presence of the magnesium. And so this is going to go 0.0862 plus S, and then 2S molar. And so we get KSP is equal to 0.0862 plus S times 2S quantity squared. I'm going to use the simplifying assumption here. So I'll get 0.0862 times 4S squared. And then calculate my S. So KSP was 1.1 times 10 to the minus, or 1.8, sorry. 1.8 times 10 to the minus 11 divided by 0.0862 divided by 4, and then I'm going to take the square root of that answer, and I see the solubility went down. Now we're at 7.22 times 10 to the minus 6 molar. I'm only allowed 2 sig figs because of K, and so 7.2 times 10 to the minus 6 molar versus in pure water was 1.7 times 10 to the minus 4. And so the solubility went down quite a lot. We aren't going to be able to dissolve as much. All right, for part C, it's a repeat of the calculation, but instead we're going to have 0 magnesium, but the hydroxide is not going to start off at 0. The hydroxide is going to start off at 0.0355. So why don't you set that up? here. And so we'll have our magnesium hydroxide, solid, goes to magnesium 2 plus 2 hydroxides. The magnesium 2 plus initial is going to be 0. Nothing's dissolved, but we already have some hydroxide present, which is 0.0355 molar. Is that correct? Yeah, 0.0355 molar. KOH is the same. It's going to be hydroxide. It's 1 to 1. So the first question is, should I double that? Should it be 2 times 0.0355, or should I just leave it as 0.0355? Do I need to double it because the hydroxide's 2? And the answer is no. It's 2 because of we're trying to relate it to MgOH, and we're trying to relate it to magnesium, but that's the actual concentration. And we leave it. Why don't you finish this calculation for me? (1.8 times 10 minus 11). For the solubility. Okay, again, this would be less than 0.1 molar, so this would be insoluble. Did you check your K value?
No, not yet.
Professor,
Mm-hmm.
what elements can be above 0.1 molarity and still, for the barium, strontium, something else?
Hydroxides are insoluble, except group 1 ammonium, calcium, strontium, barium. So calcium, strontium, barium are considered soluble hydroxides. Magnesium hydroxide is considered an insoluble hydroxide. Solubility is important. So, for example, some people consume magnesium hydroxide. You might have heard it before. Yeah, milk of magnesia. Magnesium hydroxide is considered a weak base because of its low solubility. Whereas these, if you ran out of magnesium hydroxide, don't use calcium, strontium, or barium, or sodium, or ammonium, or lithium, because those are strong bases. They have lots of hydroxide, and so these are going to be lethal. Okay. But the only reason you can consume milk of magnesia is because of its low solubility. So let's check our K value. Was everybody able to calculate this? So I'm going to go 2.8 times 10 to the minus 8, and then square that, times 1.4 times 10 to the minus 8. (1.097 times 10 to the minus 23). Did I do something wrong? Oh, I did. Yeah, I see what I did. This is wrong here. This has got to be 0.0355 plus 2.8 times 10 to the minus 8. 0.0355 plus 2.8 times 10 to the minus 8 equals, square that, equals times 1.4 times 10 to the minus 8. 1.76. times 10 to the minus 11, which is close to 1.8 times 10 to the minus 11. If we round this, it would be 1.8. And so we're okay. All right. Okay, did everybody solve for S for this? No? Yes? It's similar to part B. All right, we're going to add part D. In 1.0 molar sodium nitrate, when we look at part D here, sodium ions, do they participate in the equilibrium at all? No. In B and C, it's kind of like Le Chatelet's principle. You know, if we increase the product concentration, the equilibrium shifts left. So we expect lower solubility because of increased product concentration. But when we look at D here, D is, there's no common ion. Sodium nitrate. But it does have an impact on the solubility. It's called the uncommon ion effect. Can you remind me what the uncommon ion effect is? Did we talk about it last time? The uncommon, does that sound familiar at all or not? Andrew, no? I mentioned it, but you don't recall anything about it? To understand the uncommon ion effect, we have to go back to chapter 14. And let's go take a look at this here. This is a couple of paragraphs here. Let me read these for you. Interionic attractions. Despite its initial successes, there were apparent deficiencies in Arrhenius theory. The electrical conductivities of concentrated solutions of strong electrolytes are not as great as expected. And values of the Van Hoff factor I depend on solution concentrations as shown in table 14.4. I'm not going to talk about the Van Hoff factor or colligative properties. For strong electrolytes that exist completely in ionic form in aqueous solution, we would expect I equals 2 for sodium chloride. And for sodium chloride, we expect I equals 2 because that should split up into 2 ions. One sodium ion and one chloride ion. I equals 3 for magnesium chloride because that should split up into 3 ions. 1 magnesium and 2 chlorides, a total of 3 ions. And so on, regardless of solution concentration. These difficulties can be resolved with the theory of electrolyte solutions proposed by Peter Debye and Eric Huckel in 1923. This theory continues to view strong electrolytes as existing only in ionic form in aqueous solution, but the ions in solution do not behave independently of one another. So this is idolized. So the ions in solution do not behave independently of one another. Normally when we think about ions in solution, they're just moving independently. Instead, each cation is surrounded by a cluster of ions in which anions predominate, and each anion is surrounded by a cluster in which cations predominate. In short, each ion is developed or enveloped by an ionic atmosphere with a net charge opposite its own. See figure 1424. So if we go over to 1424, each cation is surrounded by an envelope, they call it, of anions. You see that? And what did we call this? Well, I called this a cluster, for lack of a better term. And over here, the anion is going to be clustered by positive. In an electric field, the mobility of each ion is reduced because of the attraction or drag exerted by its ionic atmosphere. Similarly, the magnitudes of the colligative properties are reduced. This explains why, for example, the value of I for 0.010 molar or mol sodium chloride is 1.94 rather than 2.00. What we can say is that each type of ion in an aqueous solution has two concentrations. One is called the stoichiometric concentration and is based on the amount of solute dissolved. The other is an effective concentration called the activity, which takes into account interionic attractions. Stoichiometric calculations of the type presented in chapters 4 and 5 can be made with great accuracy using stoichiometric concentrations. However, no calculations involving solution properties are 100% accurate if stoichiometric concentrations are used. Activities are needed instead. The activity of an ion in solution is related to its stoichiometric coefficient through a factor called an activity coefficient. Activities were introduced in Chapter 13. In Chapter 15, their importance in chemical equilibrium will be discussed in more detail. So, in other words, we should be using the effective concentration. So, you know, stuff like this, if it doesn't make sense, you just read it over and over. If it still doesn't click, then you start looking for other sources, Wikipedia, other textbooks, etc., until it makes sense. And so you shouldn't give up on things like effective concentration, you know, versus stoichiometric concentration. There are two concentrations that we deal with. Stoichiometric concentration I call the ideal concentration, and the effective concentration I call the real concentration. And that's to liken it to Chapter 6, where we talked about real gases versus ideal gases. You know. So in 1 molar sodium nitrate, this is what happens. So the magnesium ions are going to end up being surrounded by nitrates. So basically there are two ways of visualizing this. One way is via Le Chatelet's principle. Even though the nitrate doesn't react, it hinders the behavior. So we have this one. This is free magnesium. It's free to react with hydroxide. Then we have clustered magnesium. In this clustered magnesium, is it free to react with hydroxide to precipitate? No. The nitrates are interfering with this. Do you see that? And so what effectively happens is this removes magnesium from solution, and Le Chatelet's principle says as the magnesium concentration goes down, this equilibrium should shift right. So this shifts right. However, these clusters aren't so stable. You know, if these were very stable clusters like a complex, then we'd see a significant impact. But these clusters are fairly unstable, and therefore this is a very minor shift right. It's not a major shift, just a very minor. And the same thing with the hydroxides. The hydroxides are going to be clustered by sodium ions. And there's no real reaction there. It's just these electrical drag, you want to call it, or just being hindered by these sodium ions. And therefore the free hydroxide concentration goes down. Well, as the free concentration goes down, this should shift right. And so what we see is the uncommon ion effect is going to result in a very slight increase in solubility. And I drew a chart the other day where the common ion, actually it's here. When we add common ion like magnesium or hydroxide, the higher the concentration of the common ion, magnesium or hydroxide, the lower the solubility. We're going to experience a more dramatic shift to the left. However, for the uncommon, what we see is the uncommon ion, which is given by the dotted line here, we expect an increase in solubility, but it's not such a dramatic effect. Just a slight increase in solubility as the uncommon ions cluster around the magnesiums and the hydroxides, hence effectively reducing their concentration slightly. We see that. And so we end up with a weird situation. A weird situation is like this. Which of these four is magnesium hydroxide the most soluble in? Is magnesium hydroxide the most soluble in pure water? In 0.0862 molar magnesium chloride? In 355 molar hydroxide? Or in 1 molar sodium nitrate? Which would you expect magnesium hydroxide to be the most soluble in? A, B, C, or D?
A.
No, A is not correct, unfortunately. You would expect it to be. You'd expect it to be A. But because of the uncommon ion effect, it's actually D. D it should be the most soluble in. And so it's just weird. Which one is it least soluble in? You have to be careful about least soluble because it looks as if magnesium has more, but there's a square dependence on hydroxide. So you have to be careful with that. It's non-linear. And so you can't necessarily have linear thinking. And so B and C we could figure out based on calculation. And it turns out, was it B or was it C that's least soluble in? And so in B it was 10 to the minus 6. In C it was 10 to the minus 8. Turns out it's C is the least soluble, even though the concentration of hydroxide is higher or lower. Even though the concentration of hydroxide is lower, you wouldn't expect that because as concentration increases, so does solubility, but because of the square dependence, we have to be careful. We can't think linearly.
Can we not calculate D unless using activities?
Yeah, we would need, you could try D using Visual Mintech, but we are not going to be able to do that. All we can do is qualitative, and that's all the book does, is a very qualitative picture. All right, let's go on to the next problem I want to look at. So this is what I've been harping you to read, these 3 paragraphs here. But sometimes it clicks, sometimes it doesn't. So if it doesn't click, you could reread it, you know. That's the best thing. When I was taking biochemistry, the professor said to read each chapter 5 times. And initially when I started the class, I tried to read each chapter 5 times, but it was impossible. I'm too slow of a reader. There was no way I could read it 5 times. So I gave up on that, and I only read the stuff that confused me 5 times. And that was it. So if this stuff confuses you, you read these 3 paragraphs 5 times and it might click. Maybe. The other stuff I just skimmed, if I understood it. All right. And then that worked out okay, I think. But this book, the reading's very slow. It's hard to read. All right, let's take a look at number 26 next. Assume that to be visible to the unaided eye, a precipitate must weigh more than 1 milligram. So if you're only precipitating out less than a milligram, it's really hard to see. I mean, there's barely any crystals there. And if you tried to filter that, that would be just really difficult. If you add 1.0 milliliters of 1.0 molar sodium chloride to 100 milliliters of clear saturated aqueous silver chloride solution, will you be able to see silver chloride solid precipitate as a result of the common ion effect? So let's give this problem a try. Yeah. So what we're going to have to do is we're going to have to do the step I solution dilution. We're adding 1 to 100. And so the total volume is going to be 101.0 milliliters. And then we are going to have to calculate the new concentration. So let's go ahead and calculate the new concentration of sodium chloride. Sodium chloride would be a 1.0 to 101.0 dilution of 1.0 molar. All right, now they're asking us about this silver chloride solution. So what we're going to do is, for these common ion type problems, we like to reset everything. And so I would go silver chloride solid goes to silver ion plus chloride. And it says it's saturated at equilibrium, but I don't like doing Le Chatelier shift type problems. I always like to reset these. And so the way I'd reset this is I'd start off assuming nothing's dissolved. And I have 0.099.
2 zeros.
2 zeros? Okay, thank you.
0099.
All right. Chloride. So if I reset, I go initial change. Okay, what I'm going to do is I'm going to have some chloride in there to begin with, and then I'm going to let the silver chloride dissolve. Silver chloride's up here solid. I just got to make sure I have enough. So this is going to be plus S molar, plus S molar. And so at equilibrium, I'm going to have S molar silver ions and then 0.0099 plus S molar chloride. Now, having the presence of the common ion here is going to decrease the solubility because I already have a bunch of chloride in there. And so S doesn't need to be as big. And so I expect a decrease in the solubility. Versus a Le Chatelier shift. A Le Chatelier's is first I'll saturate the solution. So I go silver chloride. It's going to go to silver ions plus chloride. And initially this was just a saturated solution in pure water. And so I would go initial 0, 0, and then I'm going to get S molar and S molar. And so initially I'm going to have KSP, which is going to equal the silver ion concentration times the chloride ion concentration, which is going to be equal to S squared. And so S is just going to equal the square root of the KSP. KSP for silver chloride is 1.8 times 10 to the minus 10. So I'm going to just take the square root, 1.8 times 10 to the minus 10. Now I get 1.34 times 10 to the minus 5 molar. And so I have 1.34 times 10 to the minus 5 molar and 1.34 times 10 to the minus 5 molar. So this is at equilibrium. And then I'm going to perturb it. I'm going to perturb it by adding some additional chloride. How much chloride? 0.0099 molar. This is going to be 0 here, plus 0. Silver, I'm just adding more chloride. And so the new initial conditions will be 1.34 times 10 to the minus 5 molar silver ions, and then add these two up. So plus 0.0099, and this comes out to 0.009934 molar. All right, now I have too much, and so Le Chatelier's principle says we're going to shift it to the left. So I'm going to go minus S minus S. So I'm going to get 1.34 times 10 to the minus 5 minus S molar, and 0.009934 minus S molar here. Except the problem is I can't use S here. Do you know why? S is the amount of solid that dissolves. In this case, S is the amount that's going to precipitate. And so I can't use S here. I have to use X. So this should be minus X minus X. And so this should be minus X, where X is the amount that precipitates, not the amount that dissolves. Whereas over here I can use S, because S is going to be the amount of solid that dissolves. Now what would you rather do math-wise? Would you rather do the equilibrium that gets perturbed and then solve for the shift? Or would you reset it and just solve for the solubility? Which one looks easier mathematically? You could do either one. Will give the same answer. For the equilibrium concentrations. Ultimately, we want the equilibrium concentrations. Can you do it? KSP is 1.8 times 10 to the minus 10. Yeah, we'd like to figure out what the equilibrium concentrations are. So go ahead and calculate the equilibrium concentrations. I'll be right back. Solve whichever one you think is easier. So the reset is going to be easier, I think, to solve for the equilibrium conditions, but it's going to be harder in terms of how much precipitates. Because if we didn't reset it and we did Le Chatelier's, then X is the amount that precipitates. You know, X is going to be the shift to the left. But I don't want to solve this because this is going to result in a quadratic, and the numbers aren't so easy and clean. And so what I'd rather do is just solve this one. And so if we solve this one, the KSP is equal to S times 0.0099 plus S. And then here we could try the simplifying assumption. This is going to be S times 0.0099. And then S is just going to equal the KSP 1.8 times 10 to the minus 10 divided by 0.0099, which is going to give us 1.8 times 10 to the minus 8. All right, if we look at the percent is going to be 10 to the minus 8 over about 10 to the minus 3 times 10 squared. So this would be 10 to the positive 5. So it's about 10 to the minus 3%. So that's fine. The simplifying assumption works. And so here we can get the equilibrium concentrations, 1.8 times 10 to the minus 8 molar here. And then 0.0099 is going to be 0.0099. That's 4, 5, 6, 7, and then a 1/8 molar. So it barely changed here. So the SA was pretty good. But now I have the equilibrium concentrations here. How do I figure out how much precipitated? Well, in order to figure out how much precipitated, I need to figure out how much was there initially. And to figure out, because this is reset, recall that this is my reset. And I didn't calculate how much was there initially. I just reset everything and just let it dissolve, unless I did this calculation here. This is the amount that must have been there initial, here. And so we calculated over here. I would have had to calculate this, because that was before resetting. So prior to resetting, I had this much, because it was a saturated solution. And so I had 1.34 times 10 to the minus 5 molar silver ions and 1.34 times 10 to the minus 5 molar chloride ions. So basically what's happening here is I'm going from 1.34 times 10 to the minus 5 molar silver ions to a new equilibrium, and the new equilibrium is going to be 1.8 times 10 to the minus 8 molar silver ions. And so how much did I lose? Well, I'm going to calculate that here. And so that means I lost minus 0.0001 or 0.00001338 molar silver was precipitated. The difference. All right, so what I'm going to do is I'm going to calculate how many grams that would be. So that was 0.101 liters of solution times 0.1338 moles of silver ions lost per liter of solution. And then for silver nitrate, I have 1 mole of silver nitrate, or not silver nitrate, what's precipitating? Silver chloride. 1 mole of silver chloride for every 1 mole of silver ions. And then silver chloride weighs 143.32 grams per mole. That's the molar mass. I just copied that from somewhere. 143. So let's see how many grams. Actually, let's see how many milligrams. So I'm going to convert this into milligrams. So this is going to be 143.32. So 0.101 times point quadruple 0, 1338 times 143.32 times 1,000 milligrams per gram. And so I end up with 0.1936 milligrams of silver chloride precipitate. Is that enough to see? Well, let's take a look. It said how much was required to be visible. It said 1 milligram was required to be visible. And we only have about 0.2 of a milligram. So unfortunately we can't see it. So the answer is no. This little is too little to be visible. And so on the one hand, doing a Le Chatelier's is easier because we would have gotten X, the molarity that precipitated. But the algebra would have been harder, and so that's why I skipped it. But conceptually, maybe this other way was more difficult. All right, let's go on to the next problem we're going to take a look at. Take a look at 31C next. If we're just interested in the question, will a precipitate form or won't it? It doesn't matter if we can see it or we can't see it. We might need a microscope to see it, but the criteria for precipitation is that the QSP has to be greater than KSP. So if we're interested, will a precipitate occur, then we need a QSP that's greater than KSP. We need too much product, and it's got to shift towards reactant, and so we have to have that. If QSP is equal to KSP, or if QSP is less than KSP, then we have no precipitation. QSP is just what we're given, and so we got to see, do we have too many ions in solution, just the right amount, or not enough? So we're going to go to C here. Looking at C, we're going to have 1 drop, 0.05 milliliters, or 0.0150 molar sodium hydroxide is added to 3 liters of a solution with 2.0 milligrams of magnesium ion per liter. And so we have 3.0 liters of 2.0 milligrams of magnesium per liter. And so what we need to do is we need to get this into molar solubility. And so I'm going to convert milligrams to grams. And then get the molar mass of magnesium. Magnesium's molar mass is about 24. I think we'll just go with that. We'll look it up. 1 mole is 24.00 grams. Okay, that gives us moles per liter. So let's go ahead and calculate that. There's going to be 2 divided by 1,000 divided by 24. Molar. And then to this we're going to add 1 drop of 0.0150 molar sodium hydroxide. And so the first step in this is going to be a solution dilution. So I'm going to do it at 3,000 milliliters. And so what I'm going to end up with is a total volume of 3,000.05 milliliters. And let's calculate the new concentration of sodium hydroxide. The new concentration of sodium hydroxide will be a 0.05 to 3,000.05 times the concentration, which is 0.0150. So that's a 0.05 divided by 3,000, 0.05 dilution factor times 0.015. That's going to come out to 2.49 times 10 to the minus 7 molar. And then let's figure out the new magnesium concentration, which is going to be a 3,000 to 3,000.05 dilution of 0.0000833 molar. So 3,000 divided by 3,000.05 times 0.12340.833. .32 times 10 to the minus 5 molar. Now, this is going to form the hydroxide. So we have magnesium hydroxide, solid. This is going to go to magnesium ions and hydroxide, 2 hydroxides. And KSP for this is 1.8 times 10 to the minus 11. So what we're going to do is we're going to calculate QSP. QSP is just the given. And so this is going to be the magnesium concentration initial times the hydroxide ion concentration initial squared. So the initial magnesium concentration is going to be 8.32 times 10 to the minus 5 times the initial hydroxide concentration is 2.49 times 10 to the minus 7. And we're going to square that. Times 2.49 times 10 to the minus 7. I'm going to square that. And so I get a QSP of 5.16 times 10 to the minus 18. QSP, excuse me. So what I see is that QSP is less than KSP. So no precipitate forms. Okay, I'm going to have to add some more whatever to get things to precipitate here. In this particular case, we don't care how much precipitate forms. In the last example, we cared how many grams of precipitate form. Okay, the next problem we're going to look at is number 35. Number 35 deals with completeness of precipitation. So in this particular problem, we want to figure out how much precipitated or how much is left unprecipitated. So when 200.0 milliliters of 0.350 molar potassium chromate are added to 200 milliliters of 0.100 molar silver nitrate, what percentage of the silver ion is left unprecipitated? And so here they're talking about precipitation, so I guess we can assume that it's going to precipitate. That is, QSP is greater than KSP. So I'm not going to bother doing the calculation. So the first step is the solution dilution. And so we're going to end up with a total of 400 milliliters. And then let's figure out the chromate. The chromate concentration is going to be, well, it's a 200 to 400 dilution of 0.350 molar. So half of that is 150, 175. So I get 0.175 molar chromate. And the silver concentration is going to be a 200 to 400 dilution of 0.0100 molar, which is going to give me 0.00500 molar. So silver chromates appear solid, so I'm going to skip that. Just look at the solutions. So the silver ion concentration initial is 0.00500 molar, and the chromate ion concentration is 0.175 molar. So I could go with this, or I could figure out maybe resetting or something like that. So why don't you try to finish solving this problem? See what you come up with. How did you decide to approach this problem? Reset. Reset's the easiest. Otherwise, we are going to have to do a QSP calculation. A QSP calculation would tell you, is it going to go backwards, forwards, or is it already at equilibrium? If it's already at equilibrium, we don't have to do anything. If QSP is smaller than KSP, it's going to go forward. If QSP is greater than KSP, it's going to go backwards. Now, it depends on what KSP is. Oops, I forgot to give you that information here. All right, thank you. What did you have? 1.12 times 10 to the minus 12. All right, looking at these numbers, it looks like the QSP is going to be greater than KSP. Do you see that? And so the shift, it should go backwards. But we don't even have to do a QSP calculation if we just go ahead and reset. So what I would do is, what Tristan said, is just reset this. And so we're going to reset to get the new initial conditions. And the new initial conditions here, we have to look at what the limiting reagent is. What is the limiting reagent here? Is it going to be the silver or the chromate? The limiting reagent is going to be silver, and so we're going to lose minus 2y, and then we're going to lose minus y of the chromate, so half of that. So half of that would be 0.00250. So if I do 0.175 minus 0.00250, I'm going to get 0.1725. Okay, so we reset it to make the math a little easier, and then the change is going to be forward here, so I don't have to calculate Q. We're automatically going to see this is going to be plus 2x, this is going to be 2 plus x. But in this case, x is going to be the solubility. So rather than calling it x, I'm going to call it s, and s here. And so this instead, we'll just call it s. And plus s. And so at equilibrium, and the solubility is, if we went backwards, we would call it x. If we're going forwards, we're going to call it s. And so this is going to be 2s molar here. This is going to be 0.1725 plus s molar here. And so this is going to equal the silver ion concentration squared times the chromate ion concentration. The silver ion concentration is going to be 2s quantity squared, and then the chromate concentration will be 0.1725 plus s. All right, then we're going to just go ahead and use the SA. So we're going to get 4s squared times 0.1725, and then we'll get an s. We'll take 1.12 times 10 to the minus 12 divided by 4 divided by 0.1725 equals, and then I'll take the square root of that. And I get a solubility of 1.274 times 10 to the minus 6. And then let's see if the simplifying assumption was justified. So S is 10 to the minus 6, and the initial is 10 to the minus 1 times 10 squared percent. So that's going to be 10. This is going to be 10 to the 7th percent, or actually 10 to the minus 6. So 10 to the minus 5%. And so that's okay. No problem with the simplifying assumption there. And so once I have my S value, I'm going to plug it in back here. So I'm going to go times 2. That'll give me my silver concentration. So this is going to be 2.548 times 10 to the minus 6 molar. And then I'll do this plus 0.1725. Which is going to give me 0.172501274 molar. So let's check our K value to see. So I'll take the chromate times the silver ion concentration squared. So times 2.548 times 10 to the minus 6. Square that. And I get 1.119. 1.119 times 10 to the minus 12. So that looks good, because it should be 1.12, and we just about have that here. Now, they're asking how much remains unprecipitated. So the amount that remains is, we need the original initial here. The original initial was 0.0500, and then we see what we have left over. We have this much left over. And so the percent remaining, percent silver ion remaining, is equal to 2.548 times 10 to the minus 6 molar at the end versus 0.00500 molar at the beginning times 100%. So 2.548 times 10 to the minus 6 divided by 0.005 times 100. 0.05096% silver remains. So if I started off with 0.0500, I'm going to lose most of it, and I just have a little bit remaining. And so in addition to this, we're going to calculate the percent silver ion precipitated. So where did all that silver go? Well, it precipitated. And so that's going to be 100% minus 0.05096%. And so that gives me 99.949% precipitation. It turns out, do you know how much chromate is going to take to precipitate out 100% of the silver? Infinite. And the reason is when we look at the solubility is going to go down like this. And so we could precipitate out 99.9%, but we're still going to have 0.1% left over. But to get that remaining 0.1%, this is going to approach zero at infinity. And so it's going to take too much. And so what we say is that if we have a precipitation that's greater than or equal to 99.9%, we call this a complete precipitation, even though it's not complete. We call it a complete precipitation because it's just not worth getting that last 0.1%. We'd have to add way too much precipitating agent just to get a tiny bit of additional precipitate. So this is the criteria for completeness of precipitation. And so we call this a complete precipitation. Even though they're asking how much is left unprecipitated, we use that to figure out how much precipitated and then say that's complete. And so, in other words, if we have less than 0.1% remaining, that's complete. All right, the next section we're looking at is called fractional precipitation here. A fractional precipitation is what we did in qualitative analysis. We did fractional precipitation of the +2 and +3 hydroxides. So for example, we precipitated out the iron 3, the aluminum, and the chromium 3 cations using hydroxide, but we left the +2 hydroxides unprecipitated. And the way we did that was we adjusted how much hydroxide was present in the solution. So let's take a look at E here. 44, excuse me, not E, 44. Silver nitrate is slowly added to a solution that is 0.250 molar sodium chloride and also 0.022 molar potassium bromide. So this is a very difficult separation here. So we have a solution that contains both chloride and bromide. And what we want to do is we want to separate out the chloride from the bromide or the bromide from the chloride. And so the chloride concentration is 0.250 molar. And the bromide concentration is 0.0022 molar. Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. But what we're going to try to do is we're going to try to take advantage of a difference in solubility, like say one's less soluble than the other. If that's the case, we might be able to precipitate one and leave the other in solution. And so that's the goal. We did that with the +3 versus +2. The +3 were a lot less soluble, so we could precipitate out the +3 and leave the +2 in solution. But both of these are -1, and so it's not going to be as easy, I would suspect. But what we want to do is we want to precipitate out silver chloride and we want to precipitate out silver bromide, or one or the other. And what we'll do is we'll take a look at the KSP values here. The KSP for silver chloride is 1.8 times 10 to the minus 10. The KSP for silver bromide, let's take a look at that. Is 5.0 times 10 to the minus 13. All right, both of these ionize the same way. When I look at the KSP equation, silver chloride breaks up into silver ions and chloride ions. Silver bromide breaks up into silver ions and bromide ions. So they both ionize the same. Therefore, we could use the KSP. The KSP is telling us that silver bromide is less soluble in general. But we have to be careful because it depends on how it splits up. So if they split up differently, then this isn't so straightforward. When they split up the same, then we're okay. So less soluble. It has the same ionization. That is, they both split up into two ions. And therefore the solubility is equal to the square root of the KSP. But there's one other complication. The other complication is that these concentrations are different. So even though the bromide is less soluble, if we have a lot more common ion, and the common ion in this case is chloride, we have a lot more chloride. If you look at it, the chloride is 0.250, whereas the bromide is 0.0022. So 10 to the minus 1, 10 to the minus 3, that's 10 to the minus, there's a 100-fold difference. And so even though the chloride is more soluble, we have more common ion, and that more common ion could screw things up and make chloride less soluble. You see, because solubility depends on the concentration of the common ion. And the higher the concentration of the common ion, the less soluble. And so we have to be very careful when we make an analysis like this. We have to be careful because one, it depends on the ionization, and two, it depends on the common ion concentrations. And so the safest thing to do is this: calculate the solubilities. But we're not going to calculate the solubilities with common ion because it's a waste of time. When we have fractional precipitation, we don't need to calculate solubilities. And I recommend not calculating solubilities with fractional precipitation. With fractional precipitation, we need to do something different. And the thing that we do differently is this. We need to know at what silver ion concentration do they precipitate. So, in other words, we're going to look at the silver ion concentration required to precipitate chloride. So, in order to precipitate out chloride, we need QSP greater than KSP. And to figure out when that transitions, what the limit is, I'm going to do this. I'm going to calculate a QSP equal to KSP. And then go from there. Because I want this for precipitation. So when the QSP is equal to KSP, we call that saturated, and that doesn't necessarily precipitate. So what we're going to do here is, okay, we'll go ahead and write the KSP equation. Silver chloride goes to silver ions and chloride ions here. And what we're going to do is we're going to figure out that, okay, KSP is equal to the silver ions times the chloride ions. And what we're going to do is we're going to figure out when the concentrations here equal that. And so what I'll do is I'll solve for the silver ions. The silver ion concentration is going to equal KSP divided by the chloride ion concentration. The chloride ion concentration is given as 0.250 molar. And so this is going to be 1.8 times 10 to the minus 10 divided by 0.250. (7.2 times 10 to the minus 10). So if the silver ion concentration is equal to 7.2 times 10 to the minus 10 molar, then QSP is equal to KSP. If we bump it up, though, if the silver ion concentration were greater than 7.2 times 10 to the minus 10 molar, then QSP is greater than KSP, and we expect precipitation. Okay, so the silver ion concentration required to precipitate chloride is greater than 7.2 times 10 to the minus 10 molar. Okay, the next thing is we want to calculate the silver ion concentration required to precipitate out the bromide. All right, so why don't you calculate that for me here? Calculate the silver ion concentration required to precipitate out. What is the silver required to precipitate out silver bromide? Yeah.
I got 2.0 times 10 to the negative 12.
Is that what you got too? 2.45 times 10 to the negative 10. Anybody else? 8.2 times 10 to the negative 8. So we have three different values. Anybody else? All right, so let's see. I'll try this one. And so we know that KSP is equal to the silver ion concentration times the bromide ion concentration. So we want this to equal the QSP. So the silver ion concentration for saturated is just going to be the KSP divided by the bromide ion concentration. And the KSP for silver bromide, 5.0 times 10 to the negative 13. But the bromide concentration is a bit lower. It was what, 0.0022? Here, for the bromide it's 0.0022 molar. And so this comes out to 5 times 10 to the negative 13 divided by let's get this. 5 times 10 to the negative 13 divided by 0.0022. And I got 2.272 times 10 to the negative 10. So that's 4 different ones. Wow.
I used 5.4 for KSP.
Oh, okay. Okay. Well, Yeah, 5.0 times 10 to the negative 13. And so 2.27 times 10 to the negative 10. And so in order for precipitation of silver bromide, we'll need a silver ion concentration greater than 2.272 times 10 to the minus 10. If we have it just there, then we see that QSP is equal to KSP. If we go greater than QSP, will be greater than KSP. So which one will precipitate first? It looks like for silver chloride we need more, 7.2 versus 2.272. So silver bromide precipitates first. Because it requires less silver. And so the way we do a fractional precipitation is we start off with 0 molar silver ions. And then we just have the chloride and the bromide present. And then what we are going to do is we're going to increase the silver ion concentration. And then when we hit a silver concentration of 2.272 times 10 to the minus 10, 2.272 times 10 to the minus 10 molar, then we've saturated with respect to silver bromide. But with respect to silver chloride, it's unsaturated. And so it's unsaturated, that is QSP is less than KSP for silver chloride. Then what we're going to do is we're going to continue to increase the silver ion concentration carefully. And so we go above 2.72 and then silver bromide begins to precipitate. So silver bromide begins to precipitate. In other words, the bromide concentration goes down as the silver ion concentration goes up. We're going to continue to increase the silver ion concentration until we get to a silver ion concentration equal to 7.2 times 10 to the minus 10. So we'll increase the silver ion concentration, which decreases the bromide ion concentration due to precipitation, until we hit a max. Stop at 7.2 times 10 to the minus 10 molar silver ion concentration. If we stop at 7.2 times 10 to the minus 10 molar silver ion concentration, then this is going to be a QSP is going to be greater than KSP for silver bromide. However, the QSP will equal the KSP for silver chloride. If we continue here, that is, if we continue increasing the silver ion concentration, then both precipitate. That is, bromide will precipitate and chloride will precipitate. And we don't want both to precipitate. And so this is going to be the stopping point. So what this means is at that stopping point, how much of the bromide has precipitated. And so at the stopping point, how much bromide has precipitated? How much bromide has precipitated? So this will be our next calculation. So we stop at a silver ion concentration equal to the max, which was 7.2 times 10 to the minus 10. We don't want to exceed this, because if we go higher than this, then both precipitate. And so to calculate how much bromide remains at this silver concentration, that's just going to equal the KSP divided by the silver concentration where we stop. And so this is 5.0 times 10 to the minus 13 divided by 7.2 times 10 to the minus 10. So 5 times 10 to the minus 13 divided by 7.2 times 10 to the minus 10. And that gives the bromide concentration of 0.000694 molar bromide remains in solution, unprecipitated. And therefore we can calculate the percent precipitation by first calculating the percent that remains. And so the percent that remains is we had 0.000694 molar bromide left in solution, and we started off with 0.0022 molar bromide initially times 100%. Which is 31.56% remains unprecipitated. And therefore we can calculate the percent precipitation. And so if 31.56% remains, where did the other go? And the other went to precipitation, so that's going to be 100% minus 31.56%. which gives us 68.44% precipitation. Of bromide. So were we able to separate out the bromide completely before we had to stop? No. And so we call this an incomplete fractional precipitation. When we have complete separation, now we aren't going to have 100% precipitation, but complete separation requires, I'll put complete in quotation marks, because it's not going to be 100%. Complete separation requires 99.9% precipitation at the stopping point. The stopping point is before both precipitate, and if both precipitate, then we end up with a mixture, which we don't want. And so, unfortunately, this one doesn't work. They're too close to one another in terms of solubility. So the questions they ask here, which anion will precipitate first? Well, the one that requires less silver, which is bromide. What is the silver ion concentration at the point at which the second anion begins to precipitate? That's the stopping point. The stopping point is before the second anion precipitates. We need to stop. If we're precipitating on cations, it'd be, before the second cation begins to precipitate. And so we calculated that. C, can the chloride and bromide be separated effectively by this fractional precipitation? No, it can't. We need 99.9% before the second one begins to precipitate. Okay, does that make sense? Somewhat?
I don't understand that last question. Could you explain it in a little bit more detail, please?
Can the chloride and bromide be effectively separated? And so what's happening here is this. This is kind of like a titration. And so here I have chloride and bromide. And what I'm going to do is I'm going to add silver ions very slowly to this. So initially nothing precipitates because I don't have enough. But eventually I'm going to have enough silver ion in here that silver bromide begins to precipitate. And so the first thing that's going to happen is silver bromide will start to precipitate. And so I'm going to start forming silver bromide. The chloride doesn't, because the chloride requires much higher levels of silver ion to precipitate. And so what we're going to do is we're going to just keep adding, because the more silver I add, the less bromide I have remaining. And the more precipitation I'm going to get of silver bromide. And so I'm just going to keep doing this. But I don't want to go too far. Because if I go too far, you know what's going to happen? If I go too far, I'm going to start precipitating out both silver bromide and silver chloride. And so I don't want both of these precipitates forming. Because if both precipitates form, then I end up with another mixture. And so what I have to do is I have to stop right before silver chloride starts to precipitate. And so this is the stopping point. I need to stop here. Well, once I stop here, how much precipitated? You know, how much precipitated and how much bromide remains at the stopping point? And so that's what we need to know. Because if we could precipitate out 99.9% of the bromide at the stopping point, then it's good enough. It's pretty much separated. If we can't precipitate at least 99.9, then we say it's an incomplete separation. You know, so 99.8 would be incomplete, but it's close enough, you know, probably. In our case, we only had like 68% precipitation. That means 30% still left in here at the stopping point. So I'm going to have 30% of the bromide remains, and about 68% of the bromide has precipitated. And it's not a great if we wanted a clean, then we want 99.9% precipitated at least, and only 0.1% remaining. And that 0.1% remaining with chloride's so minor, I guess we kind of ignore it. Does that make sense?
If you were just trying to retrieve the bromide, this would be like kind of okay though?
Oh yeah, if you were just trying to retrieve bromide and you didn't care about a 100% yield, then this is fine. You know, you could get this bromide is going to be clean because there's no chloride in there. It's all bromide. We just left 30% though in solution.
To get all the bromide, you have to have a more soluble anion compound with the silver.
Yeah, to get all the bromide out, yeah, we need something more soluble than silver chloride, you know. We got to figure out something. I mean, they're pretty close. You know, 2.3 versus 7.2. It's pretty close. And so we need a bigger difference. And so we're going to do one more of these, but fractional precipitation problems. But after we talk about pH, on the impact of pH on this. And so we're going to look at 48 next. Actually, but since we don't have that much time, wanted to take the survey for the exam and find out, are you guys okay with the exam tomorrow, or did you want it on Thursday? What's the consensus say? Thursday? Actually, how many people want it tomorrow? No, just one person, 2 people. And then everybody else Thursday. How many people don't care? Okay. All right. We'll do Thursday then. That's all right. Thursday. So we'll have the test on Thursday. Tomorrow I'll do a little bit more catch up. All right, let's take a look at the next problem. The next problem is going to be 48. Well, let me read 48 here. 48 is in the section solubility and pH. We looked at problem number 15. Let's go back and take a look at 15 again. We had the common ion, potassium hydroxide. So here, the more hydroxide, the less soluble. And so you can see that solubility is going to be impacted, like for magnesium hydroxide, on the pH. The more hydroxide, the higher the pH. So the higher the pH, the less soluble. The lower the pH, the less hydroxide, the more soluble. So we can use pH to manipulate solubility as well. Because the pH is going to be related to the pOH, and the pOH is related to the hydroxide concentration here. So now when we go to 48, we're going to be looking specifically at pH here. All right, to 0.350 liters of 0.150 molar ammonia is added 0.150 liters of 0.100 magnesium chloride. So what's going to happen here is ammonia is a weak base. Weak base is going to hydrolyze water to form hydroxide. The hydroxide will precipitate out magnesium chloride as a hydroxide. But we were able to prevent this in lab. We didn't want magnesium hydroxide to precipitate in our qual lab initially, and then later on we wanted to precipitate it. And the way we prevented precipitation was by making a buffer. We made the ammonium-ammonia buffer. Remember that? 2 drops of ammonium and then add ammonia until the pH got to around 7, 8, right? So how many grams of ammonium sulfate should be present to prevent precipitation of magnesium hydroxide? So we don't want it to precipitate. In other words, we want QSP to equal KSP. We don't want it to exceed KSP and precipitate. And so we're going to try to figure this one out. So the first step in doing this is a solution dilution. So we do a step I. And so 350 plus 150 is 500. So the total volume is going to be half a liter, or 0.500 liters. And then we're going to figure out the new concentration. So the new concentration of ammonia is going to equal a 350 to 500 dilution of 0.150 molar ammonia. And so 350 to 500 dilution of 0.15. And that gives us 0.105 molar ammonia. And then the magnesium concentration will be a 150 to 500 dilution of 0.100 molar magnesium. So 150 divided by 500 times 0.1, 0.03 molar magnesium plus. So there are different ways we could do this. They're already telling us it should precipitate, but we can confirm that it will precipitate by just checking QSP. So in order to do QSP, we need the initial magnesium concentration, which we have, but we also need the initial hydroxide concentration, which we don't have. And so what are those? And then we can figure it out. And so KSP for magnesium hydroxide, we saw that before. I think it was 1.8 times 10 to the minus 11. So I recall 1.8 times 10 to the minus 11. All right, so let's go ahead and figure out how much hydroxide. And so here's the initial magnesium. What is the initial hydroxide? Well, we're out of time, unfortunately. So the initial hydroxide, we're going to have to do a KB calculation to figure that out. Okay, so anyway, we'll continue tomorrow.
All the hoses from, I use a private register. What does it say, 2 single?
After I saw that.
Didn't tell about it, this looks sweet.
Is the teacher in class?
I'm gonna have a verbal processor. If I try to, yeah.
What is the solubility of magnesium hydroxide? Adding serious tension.
How do you go?
Take this break from that. This is the last schedule ever by my life.
Oh, I the last one. My last one.
No, it's the last trick.
Hello.
I
Okay.
have a quick
Mm-hmm,
question.
sure.
This test, the number
All right. Number 5 on the practice test.
5. Yes. No, sorry, number 3. The buffers.
Okay, number 3 on the practice test. Can you read out the question? for
Yeah,
me?
I can. It's this one, and then you circle the ones that are buffers. So I get A is not a buffer. I got B is a buffer. I don't get why C is not a buffer.
Um,
Cause
yeah. C could be considered a buffer in a way.
yeah,
What forms?
the H2C2O4 and the HC2O4.
Well, in that case, why are you saying it's a buffer? Let me ask you that.
Well, I was doing the homework, and in the homework,
Mhm.
we used it as a buffer, and I would have to go.
Like this one, because HCl is a strong acid,
Yeah.
so that's gonna screw it.
Because you had the H, what's it called? The HC, the, the HC2O4 plus the H3O, and it went to the conjugate.
Yeah. In order for a buffer, we need to have either weak acid, weak base combination,
Yeah,
or it could potentially be amphoteric.
right.
And so if this were amphoteric, but this is not amphoteric, HC2O4 minus would be amphoteric. And that could have buffering action because that's both a weak acid and a weak base. But in this case, this is an acid
Right.
and this is an acid. And neither of these are amphoteric. That is, neither of them can act as a base.
But the HCl, it can go to, reacts completely to H3O plus, and then you have your H2C2O4 plus the H3O plus, and then it would go to the conjugate base.
How does this, because this one wants to donate a proton.
Yeah.
And so what we,
Oh, so it'd go to the conjugate acid.
yeah, and the conjugate acid is terribly unstable.
Yeah, that's not.
That would be the conjugate acid.
If it was just HC2O4 without the second hydrogen.
If this were hydroxide, then yes.
Yeah.
If this were hydroxide, then it would make HC2O4 minus.
Yeah.
By taking a hydrogen away, then yes. But
what if we started with HC2O4? Would that be like our base, and then it would go to the conjugate acid?
yeah,
So that would be.
that could potentially be, depends on the stoichiometry of it, what the limiting reagent and the excess reagent are. Whatever it is, at the end of the reaction, you should have a mix of weak acid and weak base, and then it'll be a buffer.
Okay, that makes sense. And then for the last one,
Uh-huh.
I can see how they're like conjugates, but I read that the concentrations can't be too far apart from each other.
Yeah.
Like, what's the cutoff there? Like, to know
1 to 10 and 10 to 1.
1 to 10. Oh, 10 to 1.
Yeah.
So I guess that falls in the range.
But the problem with this one is it's going to be 100 to 1.
Yeah, so that's what I thought, but then in the answer key, it said it was circled as yes, a buffer. But I thought no, because the difference was too big.
The difference is too big, so it depends. To have a usable buffer, you need it within the 1 to 10 to 10 to 1 range.
Okay,
But it could be a buffer, but it's going to be a very poor buffer.
it's like a theoretical buffer.
Yeah, I mean, in a sense, it would have some buffering action, but it's not going to be an effective buffer. And so the buffer range is for making an effective buffer. This would be an ineffective buffer. But you could argue that no. If you said no, I would accept it
Okay.
too. Because it's too lopsided. I said it's too lopsided.
That's what I was like, it's too large.
Right, and so that's fine. I would have given you the points for that. And so I think that one, either one would have been fine. There's one other point there, and that's the Henderson-Hasselbalch. Even though that's a 100 to 1, Henderson-Hasselbalch will still work for that particular case. You know, it's only when you get to the really extreme extremes, like 10,000 to 1, will it fail.
Okay.
Okay.
Oh,
Okay.
that's fine.
Was that it? Okay.
Yeah.
Sure. You're welcome.